Hi everyone, I'm Jian Zhang, professor from Jiangsu University of Science and Technology. My presentation title is Composite Repair Method for Internally Damaged Cylinders Subject to External Pressure. Firstly, I introduce myself. I was born in 1984. I am the Dean of School of Mechanical Engineering, Jiangsu University of Science and Technology. My research interest is deep pressure structure. I get two doctorate degrees, one from China and another from Japan. And I was the postdoctor of China Ship Scientific Research Center. And also I have some professional activities. For example, the associate editor of ships and offshore structures, guest editors of metals and frontier in materials. And also, I'm the director of key laboratory for advanced manufacturing and technique of ship and marine equipment in Jiangsu province. The contents of the presentation include four contents: background, experimental analysis, numerical analysis, and conclusions. First, background. Steel cylinder shells are often used in oil pipelines and vehicles in the harsh marine environment. The shells play a key role in many transportation, storage, and support applications. Unfortunately, these cylinders are prone to deterioration and eventually fail because of corrosion and metal loss. These damaged cylinders must be repaired to enable them to continue operating at their initial loading capacity during their lifetimes. However, conventional repair methods for maintaining damaged marine cylinders, such as fixture usage, welding, and grouting, are different and dangerous. Composite repair is a normal repair technique suitable for ocean environment. This technique is simpler than other repair methods and has been widely and effectively used in to perform inexpensive and rapid repairs. Then, research status. With the emergence of composites, many researchers have explored the performance of these materials and their utility for repair and rehabilitation. For example, seeing combined experimental analysis with finite element analysis to investigate the material properties of four epoxy growths used to infill damaged regions of cylinders. Some researchers have focused on the use of composite materials for repairing corroded cylindrical shells and achieved results. For example, Shulman and Tahiri. The experimental study validated uh, numerical results that maximum strain occurred in an undamaged section of pipeline after repair. From LIM, the full-scale pipeline burst test and finite element analysis revealed that the burst pressure of composite repair pipe increased considerably. Then, research status. Numerous studies have been performed to understand the performance of damaged cylinders after composite repair for optimizing composite repair systems. For example, the numerical and analytical results in the ISO and ASME standards indicate that repair sleeves have great thickness for small and medium feature depths. And next, lack and core. Most of these studies have focused on extremely damaged cylinders with internal pressure. However, limited study and analysis have been performed on repairs with composite materials for damaged cylinder exposed to external pressure. So in this study, an analytical approach was developed for designing a method to repair internally damaged cylinders by using composites. Next section is experimental analysis. First formula. The repair layer thickness was evaluated based on the assumption of full thickness reduction, and the repair length was determined by the sharing theory. The scheme design. The theoretical design method was validated combined with numerical and experimental methods. Repairs were designed for 3 groups of damaged cylinders, and comparisons were made among them based on the theoretical design repair method. The scheme was proposed and won. Then we perform repair fabrication. Steel cylinders were fabricated and damaged to simulate internal corrosion. Damaged area were prepared by grit blending to a grate finish. Carbon fiber plates were wrapped around in the damaged cylinders in a fixed degree, such as 0, 1990 degree stacking sequence, and vacuum cooled in autoclave. High strength steel heads were welded to each other. Next, we carry out test. Before hydrostatic test, the wall thickness and external surface of specimens were measured to evaluate the accuracy of fabrication and provide digital geometric models for the subsequent numerical analysis. This is the wall thickness distribution of specimen, as can be seen from the table and figure. The perfect regions of fabricated cylinders exhibited a satisfactory uniform thickness distribution, and the damaged region of damaged cylinders are broad. As can be seen from the geometrical deviation of figures, the pristine, damaged, repaired cylinders were fabricated with favorable repeatability and precision. The maximum minimum deviation of cylinders were plus 0.26 and minus 0.6 millimeter, respectively. The differences within the repaired region indicate fiber average or thickness. Then, from the hydrostatic pressure curves, we can see that the curves clearly indicate all of repairs are effective. The recorded pressure curves indicate that in static loading test, 3 stages occurred: preloading, loading, and unloading. The preloading time was not controlled, because the pump was operated manually. Then we carry out failure analysis. These figures are experimentally obtained collapsed cylinders. Pristine cylinders exhibited one large ellipsoidal dent and a small ellipsoidal dent, which were adjacent. One local ellipsoidal dent was observed for the damaged cylinders. Their instability locations extend from middle to both ends, and the length of buckling propagation was 60 points of overlength. And the repaired cylinders showed that one or more ellipsoid dents and actual buckling propagation from one end through the repaired area to the other end, accompanied by debonding, delamination, and rupture. The final section is we carry out numerical analysis. First, we should build finite element model. The figure is the finite elements and meshes of a repaired cylinder. The optimal mesh was established with a size of 2.5 millimeters. There are a total of about 9,000 elements and 1,400 elements for each steel cylinder and each composite reinforcements, respectively. The interface between cylinder and composite were constrained by the shearing nose. This is the figures of buckling modes. First, the linear buckling modes of fabricated specimens. The linear bifurcation modes of a given type of cylinder were consistent and repeatable. For each group of repaired cylinders, the repair was effective. The average collapse pressure of pristine cylinders was 27 megapascal. The repaired Group 1, Group 2, and Group 3 cylinders exhibited average collapse pressure of 34, 37, and 40 megapascal, respectively, which were 1.28, 1.36, and 1.47 times that of pristine cylinders, respectively. This is a nonlinear buckling loss of fabricated specimen. These failure modes were in favorable agreement with those observed in the experiment. Major failures occurs in the center of both pristine and damaged cylinder, but the buckling propagation of pristine cylinders were greater than the damaged cylinder. The post-buckling modes of repaired cylinder first occurred at the end. However, the failure modes predicted by numerical analysis were smaller than the observed in experiments. These figures are pressure deformation curves obtained for the pristine cylinders. As can be seen, initially the pressure increased monotonically and linearly, following which it is decreased. The pressure deformation curves for pristine cylinders are higher than those for the damaged cylinders, but lower than those for the repaired cylinders. The pressure deformation curves exhibited a consistent trend and present relationship between applied pressure and maximum deflation for cylinders. The pressure deformation curves observed for the repaired group 1 are given. Then we perform comparison between experimental and numerical collapse pressure. As can be seen, experimental and numerical average collapse pressure for three groups of damaged and repaired cylinders are shown in the figure. The main finding can be found. First, the experimental and numerical results were broadly consistent in that the load bearing capacity of the damaged cylinders can be fully restored and then enhanced. Second, all experimental results for buckling loads were greater than numerical results, especially for the damaged cylinders. Specifically, the errors of pristine and damaged cylinder. As can be seen from the stress distribution in scanned models, the group 1 cylinder buckled in the elastic plastic range and yielding regions of the ideal and the scanned models are in good agreement for all cylinders. The minimum stress of scanned models was less than that ideal models. However, stress concentration were clearly observed in the scanned models. Moreover, because of geometrical imperfections, the yield region of damaged cylinder extends to both sides rather than occurring in the middle region. Finally, the conclusions. An analytical method was developed for each composite materials to repair the damaged cylinders subject to external hydrostatic pressure. This method enables the determination of optimal thickness of repair on the assumption that the cylinder will only undergo fully internal thickness reduction. The feasibility of analytical method were confirmed and using numerical methods. Numerical linear and nonlinear analysis of repaired cylinders were performed. In this analysis, the collapse pressures of repaired cylinders were 1.23 to 1.58 and 1 to 1.02 times that of pristine cylinders, respectively. However, therefore, results of numerical analysis confirmed that repair design using analytical method could fully restore the loading bearing capacity of damaged cylinders. The experimental and numerical results were broadly consistent in that the load bearing capacity of damaged cylinders can be fully restored and even enhanced. However, the average collapse pressure of damaged cylinders were 125% and 107% that of pristine cylinders in the experiments and numerical analysis, respectively. Therefore, numerical simulation provided an underestimated results. For the repaired cylinders, instabilities began at one of ends. That's all. Thank you. Welcome to Jiangsu University of Science and Technology, and welcome to our university to perform presentation and carry out international communication. Thank you very much. If you have some problems, you can contact me with using my email. That's all. Goodbye.